What's up, everybody? My name is Artyom, and this is the final video in the series where I write a bytecode compiler for a small functional programming language. It's actually been quite a few months since the last video, and one of the reasons I didn't post earlier is that I got a little bit too carried away working on my OSS project called Marksman, which is an LSP server for Markdown. So if you are writing a lot of Markdown, or even a little bit of Markdown, check out Marksman, it's pretty cool. And it's also written in F#. Actually, the first version was written in Rust, but then I rewrote it in F#. And if you would like to know more about why, let me know in the comments below. But getting back to the bytecode compilers, it's actually been a few months, right? So let's do a quick recap about what happened in the previous episodes. So in the first video, I have defined a small functional programming language, which looks like untyped OCaml. In the second video, I have implemented an interpreter for this language that worked by walking the abstract syntax tree of a program. Then I started working on the bytecode compiler, and in the first video I have implemented the scaffolding for the Codegen and the VM. And the second video I added support for LED bindings and the environment. And in this final video, I am adding support for lambda abstractions, closures, function applications, and conditionals, which is, I think, are the most interesting part of the bytecode compiler. So this is a pretty long video, and actually, I think a good third of this video is spent in debugging. So if you are not interested in debugging, please skip to the parts that you are interested in. And the timecodes are here for a reason. Please use them to navigate to the parts that you are interested in. But other than that, get yourself, a good cup of coffee and get ready for a 1 hour long dive into compiler engineering. Enjoy. At this point, our bytecode compiler and the virtual machine can handle integer literals, built-in arithmetic and comparison operations, but also variables and LED bindings. Which makes it a very sophisticated calculator, but with very low utility since we still lack functional abstractions. So next thing we're going to do is add support for lambda abstraction and functional application to the bytecode generator and the VM. Now we are inside bytecode generate function. So let's handle lambda abstraction next. But before we write any code, let's stop for a moment and think how exactly we are going to compile lambdas and then execute them. So let's start with a simple code example. Let's say we have something like this. Let x equal to 5 in let f equal to x a lambda x plus 1 in 42 plus fx. So when we generate code for this program, we would generate something like this: int const 5 to put 5 onto the stack. Then we do env save 0 to save 5 as a variable x in the environment. Then we have this lambda abstraction. So the body of the lambda is some code that we need to generate the bytecode for. But the question is, where do we put this bytecode? We cannot just put it here, in line with the rest of the code, because this is not something that we should call before we need to call it, which is much later during a program execution. So it seems that first we need not just a single tape of instructions, but we actually need several chunks of the tape. When we encounter this kind of sub-procedure, a lambda abstraction, we create a new chunk and we generate the code for the lambda in this new chunk. We label it, and then we use it kind of during execution. We jump to it later on. So actually, I guess when we have these several chunks, we could, when we generate the bytecode, the final bytecode, we could kind of concatenate all of them together, kind of patch all these labels to point to the right positions on the tape. And then the VM will just, jump wherever it needs during the bytecode execution. Anyhow, observation number one is that we need several chunks of the tape rather than just a single tape. Observation number two. This lambda, when we execute the code generated for this thing, we should have some value on the stack. This value should correspond to this lambda semantically. And this is something that we will bind to name f later on. So basically, we generate the body of the lambda on a separate chunk of the tape, but on our current tape, we generate the instruction that would create this function pointer, sort of, that we will then bind to f. So observation number two is that lambda compilation should produce a value on the stack. Finally, the body of the lambda, let's modify this example a little bit. Let's say we have a equal to 7. And then we have x plus a as the body of the lambda. This body still, like to generate the code for this body, we don't actually need anything from the environment. We can generate the code without using values from the environment. But to execute this, we do need to know the environment where this lambda was defined. So basically, this value that we will have put on pushed onto the stack needs to reference the environment where the lambda was defined. So with that said, the instruction to generate the instruction that would correspond to the bytecode for the lambda might look something like this. Basically, we make a closure. Let's use the full word. This instruction needs the variable of the closure, the bound variable, and it also needs the pointer to the body of the closure, which is going to be some label or number of the chunk where this body was generated. So it would look something like this. And then this instruction would create a new kind of closure value in the VM using the current environment and the code pointer and the variable name. Whew. So I think this kind of conveys the general idea. Let's see how exactly this will look like when we try to implement it. First, let's try to modify the generate function to accept the chunk number that we need to generate the code into. So we add another parameter here. I wonder if we can do the refactoring. Oops. So let's define the type. At this point, we are at the top level generate bytecode function, and we need to provide some chunk number here, but we don't actually have it. So let's perhaps create another helper function here. This is just a stub, but we can now use it to change to kind of complete this generate bytecode function. So we have the bytecode builder, then we create an entry chunk. And then we generate the bytecode into this entry chunk, starting with this entry chunk. Cool. Now, if we go back to our abstraction, what we need to do is we allocate a new chunk. Let's use label L for the lambda body. And I guess one thing that we need is, if we try to create the chunk with the same name, the name will be properly kind of unified by adding some unique ID or whatnot. So this will always create a new chunk. Then we generate the code into the lambda chunk for the lambda body. And when we're done, we need to basically get the number for the variable from a constant pool. All right, so let's take a step back. So we create a new chunk for the lambda. We generate the code into this lambda, into this chunk. Then we should generate another instruction in the current chunk to create a closure using the label for the chunk. So actually, let's do it like this. So we have a chunk num and a label num. Then we need to emit another instruction in our current chunk to create a closure. First argument will be the variable of the bound variable of the closure, and the second will be the label of the lambda body. Now let's try to handle the application. This actually probably much easier. So first we generate the bytecode for the argument. And then we need to emit another instruction. Then we generate the bytecode for the expression. And then we need to emit the instruction to apply the expression to the argument. So here our stack would look something like this. Here it would be, and this instruction would just take two values from the stack and run the application. So let's go to the instruction and create the apply. Perhaps one thing that we're missing is when we create code for the lambda body, we will need to jump to this code during the application. So we jump to this code pointer, we execute the code, but then we also need to jump back. So we need to return to where we were before. So let's introduce another instruction called return. And we will use this return here. So we generate the code for the body, and then in the end, we just emit one more instruction to the body chunk. And this instruction is return. All right, so this I think looks good. The only thing that's missing is actual chunk creation and this kind of label management. So let's change things a bit here. So our bytecode buffer will become bytecode chunks. So now we need to do something about kind of this label management and this thing that I talked about, where we can create multiple labels, but they will be unified, as appropriate if the names are the same. So let's introduce another helper class called label manager. So what label manager does, it takes label names, then it makes sure that the name, the actual label name that will be inserted is going to be unique, and then it inserts the new name into the pool and gives us back the number of the label. So now we can go back here and fill in the actual function body. All right, and now is actually the hard part. So what we have in the bytecode builder is this kind of a list of chunks of instructions. And what we need in the bytecode is a flat array of instructions. So we need to do two things. First of all, we need to concatenate all these chunks into a single array. And then we also need to resolve these labels to the actual position of the instruction in this final array of instructions. So here we add this mapping from labels to their respective chunks. And we will use this mapping to kind of flatten out our bytecode. But first of all, we need to change the code in the alloc name chunk to bind the new label to the respective chunk. So now in the build function, let's create something called label offsets. This will map labels to the actual offsets in the flat bytecode array. And so the idea would be to just take all the chunks and concatenate them without any sort of reordering or anything. I guess it would be interesting to see if, you know, things could be optimized by reordering chunks and make sure that, you know, chunks that are used together are close to each other and stuff like that. But here we don't actually need this to make things working, to make this basic stuff working. So let's just use the most simple approach, concatenate all the chunks without reordering, and then and calculate label offsets as we do it. So at this point, we have all the bytecode in the flat bytecode array, and we have offsets for the beginning of each chunk, which will allow us to resolve labels. That's what we're going to do now. So at this point we have the bytecode and we have the label offsets. So what we need to do is actually go back to the bytecode definition and change it a little bit, so that we have the bytecode itself. Let's call it actually instructions. And we have labels. So I think in terms of bytecode generation, we should be good. And so now is the time to go to the VM and actually handle all this extra complexity around labels and jumps and whatnot. We have several new instructions: make closure, apply, and return. Make closure instruction will create a new type of value named closure. So let's add this type of value first. Closure we'll have the environment. It will have the variable name and also the code pointer. So let's go back here and add handling for make closure instruction. All right, pretty straightforward. Now let's handle the next one, which is apply. So apply instruction takes the value from the stack. This value should be a closure, and then since this is a closure, actually takes two values from the stack. So first, let's refer back to the bytecode generation. So first, top of the stack is closure, then it's the argument. Now, as we have the closure and the argument, we need to create the environment, the new environment for the closure. And then we jump to the body of the closure. But before, we need to save our current environment in the environment stack. So let's do this. So at this point, we have updated the environment, we have saved the previous environment, but what we also need to save is the current code pointer. So, I mean, let's add another stack and let's call it return stack. We have too many stacks, but since this simplifies implementation, let's just go with it. Perfect. And now we have just the final instruction called return. So when we return, we need to restore the environment. And we need to restore the code pointer. And I think that should be it. All right, so if we take a look at +42 and +n, I think at this point we should be able to unlock both these examples. So for Fibonacci, we still need to handle conditionals, but these two should probably work. Well, let's run and see how it goes. Huh. Well, I guess something didn't go well, because now all the examples don't work. Well, let's debug this. Huh. Hey, where's my bytecode? Alright, so this seems to happen actually during bytecode generation. And I bet this is happening during bytecode build. Line 191. Okay, let's put a breakpoint and see what we have there. This is such a landmine, or a foot gun, or whatever. Of course, I was comparing things rather than replacing things, so surely things didn't work. Oh my god, it's it's fascinating how these small things can trip you up. So let's run again. Aha. Aha. Well, there's progress. There's progress. Looks like something's wrong in the bytecode. Okay, so at this point we try to apply plus 42 closure to 3. So we create a new environment, closure env, that has mappings both for plus 42 and for 3 for x that is equal to 3. To push the current environment, we update, we save the code pointer, and then we should go to 6. So code pointer should be equal to 6 now. Yes. So the current instruction is envload. So we need to load 3. Okay, fine. We'll push 3 onto the stack. We have 42. Three, 42, and then addition. Okay, fine. Addition. We pop both arguments. We have the result, 45, push it back into the stack. And now we need to return. Yes. So we go to the return, we restore the environment, we restore the code pointer, then we drop one lead binding, And at this point, we actually passed over the program's end into the lambda body. So I guess this is the point where we could really use our halt instruction that we defined at the very beginning to mark the end of the execution. Wow, this bytecode stuff is really tricky. So let's see. So let's add another instruction here. All right, so let's see if this actually helps. Well, it did help with plus 42 example, and it seems to still fail with plus n. What is different there? So we have two lambdas, one inside the other, and then we do a couple function applications. We have this error here that some variable name is not bound. And this happens only in plus n and doesn't happen in plus 32 example. So the difference is that in plus 42, we have just a single lambda. In plus n, we have actually nested lambdas. So lambda inside a lambda to implement x plus n. So let's run the debugger and see where it may go wrong. So we make a closure. That's fine. We save it as plus n. We push the arguments to the stack. That's 5 and 3. Then we load plus n from the environment and onto the stack. And then we do a couple applications. So if we take a look at the bytecode, that's exactly what happens. Make a closure. We load 5 and 3 onto the stack, load the closure from the environment, and do the applications. As you see here, we apply plus n to 3 and to 5. All right, so far so good. So let's see, we take the closure. We pop the argument from the stack. Our closure environment. All right, so our closure environment here has 2 arguments, while in fact it should have just 1. Okay, our closure shouldn't have the mapping of itself to plus n, and I guess that's where the issue is. So when we create the environment for the closure application, we should take the environment that closure captured, not the current environment. So let's stop here and adjust this code. Okay, let's run again. And look what we've got. So plus 42 works and plus n also works. So now we have just a few things left actually. So we have the conditionals, and we also have this extra piece about kind of recursive bindings. So last time I said that since we don't have closures yet, this EnvUpdate doesn't do much. Well, now we do have closures, so let's implement the EnvUpdate instruction properly. So we take the value from the stack. Then we need to create this new environment. And then if the value is a closure, we need to update its environment to this new env. So let's do this. So we need to take the environment of the closure and we need to update it to env. So this is not currently mutable now, but we can fix it. Then we go back. And otherwise, we do nothing. All right, looks good. So now to the remaining bit, which is the conditional. Let's start with the code generation first. All right, so let's think about how to compile conditionals. First of all, we have the predicate, and we need the value of a predicate before we decide whether to go to the true branch or the false branch. So this part is pretty clear. We generate the code in the current chunk for the predicate. Then we have true and false branches. So what we could do is the following. If the value of the predicate is true, so let's say we have let's assume the code goes from left to right, the instructions. So we have the predicate instructions here. And then we could generate the code for, let's say, false branch. Followed by a, let's say, jump instruction to the continuation label. And then we could generate the code under another label, which we'll call true branch label, for the true branch. And then we will have the cont label. I guess one issue here is that we don't have any instruction to bind cont label to, but this is again something that can be easily solved. We can introduce another instruction called no-op. So I think this should work. So overall, we need two instructions. So it's gonna be jump true, just unconditional jump, and the no op. So jump true will jump to the label if the value on the stack is true. Jump will jump to the label unconditionally. Let's maybe remove this. And then we have the no op. Another interesting thing here is that here we need to create some labels, but we cannot bind them to any code pointers at the beginning. We will only be able to do this when we generate the code. So let's create a couple more functions. So the first one will be or maybe just one function, bind label, and it will take the label number, and then it needs a code pointer. So currently we map labels to chunk numbers, which is I mean, it worked before, but now we need something a bit more precise. So a chunk number plus the offset inside the chunk. So let's introduce another type, and it will be like this. Then here we can just do something like this. Good. So let's generate the labels. Now we generate the code in the current chunk for our false branch. Then we emit the instruction to jump to the count label. Now, at this point, we have the offset for the true branch instruction. So we can bind the label to the offset within the current chunk. Now we generate the code for the true branch. Now we can bind the count label. And finally, we meet the no-op instruction. All right. Let's see what is missing here. So these are now chunk pointers. So we need to change this a bit to use the offsets as well. Perfect. And now we just need to add a couple more instructions to the virtual machine. First, we start with jump true. So this means we need to make a jump. So we need to update the code pointer, label offsets, label. And that's it. Now the jump instruction even simpler. And finally the no op instruction is basically a no. Okie dokie. So, well, let's see if it works. If it works, then we will effectively unlock all the things from the example programs. Fibonacci with direct encoding, with fixed point encoding, and yeah, everything. Cool, let's see. All right, so now it gets stuck. Perhaps something's wrong with these environment update function. So let's put a breakpoint here. Oh. All right, let's take a look at the Fibonacci source code first. Something's odd here in terms of the bytecode shape. So we have two chunks. that's kind of the main routine. And this is the body of the Fibonacci function. Oh, that's weird. Let's see how we generate code for the conditional once again. All right, so we have the expression. So if this thing is, if n is less than 2, then we return 1, otherwise we do the recursive part. So we are in chunk number 1 right now. No instructions here just yet. So we generate the code for the predicate. That's the code for the predicate. Then we create 2 labels. Oh my god. I forgot to emit the jump through instruction here. All right, let's try again. Just look at it. It works. It worked. Maybe the error reporting in the last case is not as good. That could be easily fixed. But other than that, it works in simple cases. Some multiple applications of lambdas. So Fibonacci works fine. And it's actually quite a bit faster. Well, given how much more effort it took, that's kind of expected. This is it. We now have a fully functional bytecode compiler for a small or camel-like functional programming language. I'll wrap up with 2 remarks. First, although we do have the Codegen, the bytecode, and the virtual machine, right now everything in Fang happens in memory. A next logical step could be to implement a serialization of this bytecode, dump it into a file on a disk, and then maybe implement the virtual machine in another programming language like Rust. That would be an interesting exercise, and the one that would allow to achieve this true decomposition between the code compilation and code execution. Then second thing is the fact that the bytecode as it is right now in Fang is really far from being optimal. In particular, functional application, which is the thing in FP, is really heavy right now because it involves a lot of manipulations with maps. And with a little bit of time and energy, it could be optimized. Actually, in the real world, we would probably have another layer between the AST and the Codegen, the intermediate representation, where we would do, the majority of transformation and optimizations to get the maximum performance out of this language. But this doesn't really change the fundamentals that we've covered in the videos so far. Now, since this is the series finale, I'll give a quick round of applause to myself and to you for making it to the end. Thank you very much for watching. I hope this was helpful. See you next time. Peace.